Okay, so I am now recording. So the last section of the tutorial is about push-down automata, specifically non-deterministic push-down automata. So what is a push-down automata, or also known as a PDA? A non-deterministic push-down automata, or NPDA, is defined as a 7-tuple M, which has sort of the following components. So it has a similar definition to PDAs, DFAs and NFAs, except it has a couple of new sort of features to it. So for instance, the components in M are Q, which is a finite set of states, sigma, which is the input alphabet, so it's the same alphabet as you would see in an FA. A component that is different, though, is capital gamma. Capital gamma is a finite set of symbols, which is used for the stack alphabet. So I'm going to discuss the stack in a few seconds once I finish sort of describing the definition. Then I have delta, which in this case is a transition function that takes a state, a symbol from the alphabet, or a lambda transition, and a symbol from the stack, and then it produces, or it gives you a finite set of subsets of states and of stack strings. Okay. Then we have an initial state, which shouldn't be in sigma, it should be in Q, which is the initial state, so that's where you start. It's very similar to an FA. Z, which belongs to the alphabet gamma, is the stack start symbol, so that's a bit different. That's something we haven't seen yet. And then F is similarly to FA's a set of final states. So if you just want to think of a PDA very broadly, you can think of it as, first of all, an FA. An FA, really what it did was, you can think of it as having a control unit. And then what the control unit would do is it had some input tape, and the control unit would essentially just read the input tape. So for example, if you had A, B, BA, if this was just an FA, then it would read A, B, BA. It would do some computation here and end up in a final or non-final state. But now so that's for an FA. Before a PDA, you have the control unit and the input tape, but now you also have a stack. So for the stack to exist, it has to have an alphabet, so that's why we have gamma. And we also define a stack start symbol, Z, just so we know where the bottom of the stack is, okay? Because stacks work with pushing and popping, so we want to know what the bottom of our stack is. And then what happens is, when you have a transition from one state to another, not only is the control unit going to read an input tape, it's also going to look at the top of the stack. So it's going to look at the top of the stack, and then it's going to replace it with another sort of set of stack symbols. So for instance, if you were in this state here, let's call that Q0, and you went, so you transitioned to Q1, let's say by reading an A. So far this is very similar to FAs, but now what you're going to do is, suppose my stack has some contents. Let's say the stack looks like X, Y, X, okay? And what this is going to say is, if you're in Q0 and you read an A, and the top of the stack is, let's say, X, so this is the top of the stack, then I replace X, or I I pop X and I replace that with, let's say, Y. So then you would go from this stack, you would go to another stack that looks like X, Y, Y, and now you would be in this state here. So not only do you transition in your state, you also transition in your stack, okay? And this becomes a very powerful tool for accepting languages that could not be accepted by F8s. But before that, oh no, actually, with that, let me give you an example. So suppose I have the following transition rule. If I'm in Q1, so we can write the transition function as if I'm in Q1 and I see the symbol A on the input tape and I see the symbol B on the top of the stack. So this is your current state. This is your input symbol. And this is the top of a stack. Then I have two options. Either I replace B, I transition from Q1 to Q2, and I replace B with CD. So that would look like something like I go from Q1 to Q2, and now the new top of my stack is CD. And by the way we read this is from left to right. So CD on the stack would look like the CD and something else. And then you would have the start symbol of your stack. Okay, so that would be for that transition. Or the other thing you could do is if you're in Q1 and you read an A, then you could, and you have a B at the top of the stack, then you would replace that with a lambda. So this sort of transition in your stack essentially just refers to popping B. So for instance, so this would look like if I'm in Q1 and I read an A and the top of my stack is B, then I go to Q3 and the new top of my stack is lambda, but really lambda is only sort of telling you what the replacement is. So what that means is if in Q1 I had something like B, and then let's say I had A, B, A, and then Z, then what would happen is I would take this B and I would pop it. So I would go to Q3, and now my new stack looks like A, B, A, okay? And the sort of top of the stack would be essentially what was below the B. So it would be everything below the B, okay? So that's how the transitions work in PDAs or in NPDAs. So let's look at a few more definitions before we look at a concrete example. This is something that you'll also probably see in tonight's lecture if it hasn't been covered yet. It's for describing the state of a PDA. So we have the definition here. We have the instantaneous description of a PDA is a triple QWU, where the first component of the triple Q is the current state. W is the input string left to read, and U is the current state of the stack, which again you would read, you would sort of read from left to right. So for example, if you have an ID, so you can sort of just call this an ID. If your current ID is Q1, BBA, and let's say, I don't know, something like X, Y, X, and then let's use the $sign for the bottom of the stack. Then this means that you're in Q1, what you have left to read in your input tape is BBA. So this is what's left to read. and the sort of contents of your stack are X, Y, X, and then $sign. Okay, so you read this from left to right, basically. From left to right and from top to bottom. Okay, so that's what your ID is, essentially a description of your current state. And the reason why this ID is useful is because we use it to represent transitions in your sort of PDA. So for example, if you want to represent a transition delta, so this is to represent sort of if you're in Q and you read an A, okay, replace the top of the stack, which is B, with Y, and then go to P. So if you want to represent this, because this is not very compact, if you want to represent this more generally, more compactly with instantaneous description, you could say this is your current state Q. What you have left to read is A plus some other string. So you have AW left to read. And the top of the stack looks like B is at the top, and then X is sort of the rest. So you have A and then W as the rest. And then you have B at the top and then X on the bottom. Then you transition, you go to the next state P. Now you have only W to read. So your arrow is now here. And now you replaced B with Y. So this would be how you would represent this. This is the ID representation of this guy, which becomes helpful. It becomes helpful when you want to define what the language accepted by M is. The language accepted by M is the set of strings over the alphabet sigma star, over the alphabet sigma, where if you're in your initial configuration, so you're in your initial state, you have all of your string to read, and you have Z as the start of your stack, at the bottom of your stack. Then if there is a ID transition, so this is just an ID transition, any number of IDs that allow you to go to P, where P is a final state, and you have finished your, so you have lambda left to read, meaning your input state, your input tape is done, you've finished reading it. Then W is, that string W is a part of the language accepted by M. And all such strings are going to form the language accepted by M. So what's important to notice as well is that the contents of your stack U can be anything. So it doesn't matter what you finish with in your stack, as long as you finish finished your input and you ended up in the final state, then you accept that string. Okay, so this might seem like a lot to sort of take in, and I understand that, but sort of just remember that this is just referring to a more compact representation of saying that you're in Q0, and then you wanna read W. So you're going to read W. Let's say W is x1 to xn. So you go through a bunch of transitions, x2, and so on to xn, okay? And because now it's a PDA, we're also going to consider the contents of your stack. So you're going to start with the contents of your stack. So here the contents of your stack is going to be Z. And then as long as you sort of keep going with your stack having something in it, and you finish here with U as something in your stack, if there is a transition that looks like this, then that means that your string W, which is x1 to xn, is accepted. Okay, so this is just a more a formal way of representing that notion. Okay, now let's look at a concrete example to maybe make this clearer. So the following PDA here is actually a PDA that's going to accept AM, BM for m greater or equal to n. And let's actually go and see why. So for the purposes of this example, suppose that we already have in our stack the dollar sign at the bottom of the stack. So typically what you would need to do is you would need to initialize that with something like this, okay? But just for the purposes of this example, we've omitted that and we assume that we start at Q0 with this guy, with that initial configuration. So what is this saying? This is saying that we accept any number of A's followed by any number of B's, where the number of A's are followed by B's. Okay, so why is this true? Well, let's look at a sort of input string. So we have the input string AA, BBB. That's something that should not be accepted. Okay, we know that the contents of their stack are initially the dollar sign, and the state is we start in Q0. Okay. So I'm going to use this box to help me look at the stack. So I'm in Q0, okay, and I see an A. So I'm going to choose to read an A here, okay, and then I'm going to read an A, and this guy is going to tell me what I do to my stack. What I'm going to do to my stack is I'm not going to pop anything, but I'm going to push an X. So what's going to happen is I'm going to push an X, and X is going to land in my stack. Okay, so then the new contents of my stack are going to be X dollar sign, and now I'm at the second A. So I'm at the second A, I'm going to stay in Q0, read that second A, and now I'm going to have another X that's going to be pushed. So I'm pushing another X. Okay, so now I'm done reading my A's. So I'm done reading my A's. I'm going to use this lambda transition, which doesn't read any inputs and doesn't modify the stack. So my stack is going to stay the same. Okay. And now I'm going to read the input symbol B. So I'm in Q1. So because I'm in Q1, it doesn't necessarily mean that I'm going to accept the string. Okay, and you'll see why. Because now the contents of my stack are XX dollar sign. So now I'm in Q1. I read a B. If I see an X at the top of my stack, I pop. So I pop the X and I push a lambda. So really this just is analogous to saying I pop an X. So I'm going to essentially remove an X. I'm going to remove an X here, and the contents of my stack are going to be X and then dollar sign. And then again, I'm going to read another B. I'm going to use this transition and pop another X. So now my stack is essentially empty, but I'm not done looking at my input. I have another input B, but now I'm in Q1. The only way I can read a B is by reading a B here, but I can't use this transition because for this transition to occur, the top of my stack should be X. The top of my stack should be X, but I see that the top of my stack is in fact the dollar sign. So I would not be able to use this transition. So I would essentially be stuck, and this would allow me to reject a squared b cubed. If, however, I had something like a cube b squared, then you can sort of see what would happen. You would read 3 a's here, and then your stack would fill up with 3 x's. Then you would transition to Q1. You would pop, so you would pop this x, you pop this x, pop this x, and then you would be done reading your you would be done reading your input. It doesn't matter what the contents of the stack are at the end, as long as you finished your input and you're in a final state, which is what has happened, and so that would have been accepted. Okay. So that's an example of walking you through a PDA. All right. So now an exercise for you. What symbols should be in the stack after the following transitions, where we have sort of these contents in the stack. So remember, CB is read left to right, so this would look like CB $. So I encourage you to pause the video and to have a try. Okay, so hopefully you've had some time to look at the exercise. We're going to sort of go over the solution together now. So this was just to make sure that you weren't really lost in the explanation of the transitions of the stacks and the input tape. So let's have a go here. We have the following transition. Q1, when you read an A, and at the top of the stack there's a lambda, so this is always going to be true. Then transition to Q2 and replace lambda with C. So really something that would look like something like Q1, when you read an A, you replace lambda with C, okay? This really just corresponds to push C. So then if your stack looks like B $, then your stack is going to look like a CB $, okay? And then sort of the same idea, but in reverse here. Here it says that you're in QA, you read an A on your input tape, and you see a C on the stack, at the top of the stack. Then replace that with lambda, but that just means pop the C. So here you're going to have CB star, and you're going to pop the C to get C, sorry, that was probably not clear. So you're going to have CB star, and you're going to pop the C, so you're going to get B star in your stack. The next one is if you're in Q1 and you see an A, then transition to Q2, having a lambda as the sort of popping symbol and a lambda as the pushing symbol. So this, when you have a lambda on both sides of the arrow, that means that the stack remains unchanged. So then your stack would still look like CB $, okay? And then the last one here is you have an A and you read a $, and you replace that $, with a lambda. So this sort of translates to popping a $. So what would happen here is you would have a $, and then you would just have an empty stack. Sorry, this is a P. No, it's not. Okay. Empty stack. So what's super important for you to remember is no transitions. No transitions are allowed once the stack is empty. Okay. So if, for example, you have your sort of push down automata here, and you do a bunch of computations, and they all lead to this guy here, where you see a lambda, and you replace the lambda, the $, with a lambda. Now you're here. Now, if you have any other transition here, it's never going to sort of be able to go there. It's never going to be able to go to this state from this state because the stack will be empty. So this is a kind of exception case. Even if you have like lambda to lambda, essentially you've sort of broken your machine. So you're not allowed to do any transitions from there. It's essentially always going to be stuck here. Okay, so that's a good FYI to know. Okay. Now the last two exercises of this tutorial are really just about designing PDAs. So I have the following exercise here, and as usual, I encourage you to pause the video, and we'll look at it in a few seconds. All right, so hopefully you had some time to think about the solution. I'm going to give you at first the idea behind this PDA, and then hopefully you're going to see how it translates to the actual transitions very naturally. So what this is telling you is it's telling you you have a bunch of A's and then a bunch of B's. Okay, you sum those A's and B's, and then that sum should be the same as the C's. So let's say you have 2 A's, 3 B's, and 5 C's. And what you can do, or what you can think of doing, is you see an A, so you have your stack, you see an A, and let's say you add X. You see another A, you add an X, and you do that for any number of X's you see. Then once you're done the A's, you go to B's, you see any number of B's, and for each B, you add an X to your stack, okay? And then once you finish the A's and the B's, and now you're going to start looking at your C's, the size of the stack is going to equal I plus J. Okay? So now what you can do is very similarly to A and Bn, for each C that you see now, you're going to pop. So for each C, you're going to pop an X. And so in this case, it turns out there's exactly 5 C's. So you're going to pop exactly 5 C's, and you're only going to go to a final state if once you're done reading the output, you have a $sign. Okay, so how do we do this? Well, let's start at our initial state. As I said, sort of in all PDAs, you actually do need to specify what the bottom of the stack is. Okay, so this example here, that was sort of an exception. We just did that to show you how the transitions work. But really, if you want to design a correct PDA, you start in your initial state, you read no input, and from the bottom, from your empty stack, so your stack is empty, you add a $sign to show everyone that you have to show that as the marker for the bottom of the stack. Okay. Now this is going to be the loop for A. So you're going to loop for A, and for each A, so you're going to loop for A, you're going to read an A, and for each AUC, so for each AUC, you're going to push an X. So remember, this is equivalent to pushing X. Okay. So now you're done pushing all the X's. You're going to use a lambda transition. In this case, a lambda for the inputs, and also a lambda for the stack to go to B. So this is going to be the loop for the B. So in your B, you're going to use the same idea. For each B, you're going to push an X. Okay, so this is pushing an X. Then you're going to transition to your loop for C. The loop for C is going to, again, read a C, but now for each X you see, you're going to pop, for each C, I shouldn't have said C, for each C you observe, you're going to pop an X. So you pop an X, and this is the notation for popping an X. And so if your string W is, so for instance, if you have A2, B3, C5, after this process, what you should have, so you have dot, 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 after this process, you should have the $sign, okay? Because you should have popped the same number of A's and B's as C's. So now what you can do is to make sure that you do have a $sign, you check that you have a $sign, and then it doesn't really matter. You can either say you empty your stack, or you keep the same symbol in the stack, or you just replace it by something else. It doesn't really matter. But what does matter is that you make that final state that last state a final state. And so if you want, we can check, for instance, lambda is going to be accepted here, because if you start here, you read a lambda at no cost here, you go to A, you read a lambda at no cost and you go to B, you read a lambda and you go to C, and then you read a lambda and you go to your final state. And that's fine because you know that 0 plus 0 is 0. Okay. Then something like A, B, C2, you would go from your initial to A, that would give you a dollar sign. You would read your A, which would give you an X. Then you would go to B, you would read your B, that would give you another X. And then you would go to your C, you would pop two C's, you would get a dollar sign stack, and then you would be able to go to your final step. And so we see that this is in fact a PDA, a PDA-M such that LLM is equal to L. Okay, now the last exercise of this tutorial is maybe a bit more complicated, but take again a few minutes to try it yourself, and we'll solve it together. All right, so now hopefully you've taken a few minutes to try to sort of think of a way of creating a PDA. But what I'm going to give you before I sort of write the transition is, again, some intuition as to how to do this. So here we have A2N, B3N. So for example, we would accept something like A4, so that would be N2, B6. Okay. So really what this is saying is you group your A's into 2s, and you group your B's into 3s, okay? And then for each A, you would push an X. So for example, for each 2 A's, sorry, you would push an X. You push another X here. And then for each 3 B's, you would pop an X. So this 3B here, you would pop an X. And this 3B here, you would pop an X. The only thing you need to sort of realize is to see 2 A's, it's very similar to the sort of concept in FAs where you have a multiple of 2. Remember, for multiples of 2, you can draw something like this, where this is your multiple of 2. And then for multiples of 3, you want something like this. So this is like 0 equals n mod 2. And this would be 0 congruent to n mod 3. Okay. So you need to sort of use these two structures in your PDA to allow yourself to see for every 2 A's, you push an X. But once you see that structure, it becomes relatively simple. Okay. So again, you start in your initial state, and if you have a lambda transition, well, you need a lambda transition because with the lambda transition, you give yourself the dollar sign as the bottom of your stack. Okay. So now what you need to do is you need to use this mod 2 cycle to give yourself for every 2 A's. So for every 2 A's, you push an X. So what you're going to do is, well, I'm going to use that cycle. So I have no choice to have this structure. And then I know on my input tape, I'm going to have an A here and also an A here. The only thing I need to decide is how am I going to, for each 2 A's, I'm going to push a single X. So what I can do is if I'm starting here, I have sort of a multiple of 2. Then I go here, okay? Let's say I don't change anything to my stack. So now I go to this. Now this is not a multiple of 2, so it's n mod 2 equals 1. So this is n mod 2 equals 0, n mod 2 equals 1. And so now if I go back, so if I go from here to here, then what I can do is, now that I'm back here, I know that I've seen 2 A's. So because I've known I've seen exactly 2 A's, now I can push an X. Okay. And then you can see that this is going to work for, let's say, A8. So A8 occurs, so there's 4 times 2, so there's 4 times a cycle of 2. So you're going to go through this guy once, then your stack is going to get an X. This guy a second time, it's going to get another X. this guy a third time, it's going to get an x, and this guy a fourth time, so it's going to get an x. So A8, which is equal to A2 times 4, so your n is 4. Here your n is 4, and here your stack has n equals 4 x's. Okay, so you've started the correct procedure of getting for each two a's a single symbol x. Okay, so that's how you would do this guy. And so if you didn't see a very obvious pattern now, then hopefully you can do the same thing for when you see multiples of 3. So this is going to be for your A. So now I'm going to use a lambda transition for my input and my stack to go to B. And then I'm going to use the same concept. So this is going to be n mod 3, 0. I'm going to have n mod 3, 1, n mod 3, 2. And this is going to go back to n mod 3 equals 0. Okay. So what do I need to do? There should be an A here. What I need to do is, well, if I see a first B, I'm not going to change the stack. If I see a second B, I'm not going to change the stack. Once I see the third B, if I know there's an X on top, then I'm going to pop it. Okay. And this cycle is going to allow me to do, so for example, if I have A8, and then, so this is B, so I need to have B12, right? Because 12 is 3, or no, I need, yeah. So I have 3 times 4. I need to pop 4 times. So that's what's going to happen. I'm going to start at B, go through here, and then pop once. Then go through here again, pop another time, and then pop a third time and a fourth time. And then if I see that my stack is only having the $sign at the end, then I can say for certain that I've seen for each 2 A's, I've seen 3 B's. So that means that I can say when I see a lambda and I see a $sign at the top, then that means I do have A2n, B3n. So now you can sort of pick whatever you want. You can use a lambda or just a $sign. And then that's going to give you a final state. And that's going to allow you to have A2n, B3n. Okay. So hopefully that's clear now. And this sort of concludes tutorial 9. Again, I'm sorry I went over the time and I had to record this, but 50 minutes really isn't that much. Okay, so see you next time.